Forget everything you thought you knew about a world ruled only by giants. 145 million years ago, the planet entered one of the most radiant and most bizarre chapters in the history of life, the Cretaceous period. As the continents began to drift apart, geographic isolation created vast natural laboratories where evolution experimented with some of the strangest life forms we have ever encountered. From armored titans like Ankylosaurus to Therizinosaurus, a plant eater armed with claws nearly 1 meter long. Alongside the dinosaurs, flowering plants emerged and spread, transforming ecosystems on a global scale. Why did evolution favor such extreme forms? What forces drove these creatures to push beyond what once seemed like the limits of biology? We are about to step into the world of the strangest dinosaurs of the Cretaceous. The secrets buried beneath millions of years of fossilized stone are about to be revealed. Picture a field in the late Cretaceous, about 75 million years ago. Not grass as we know it today, but dense shrubs, towering ferns, and conifers interwoven with something entirely new in biological history. Flowering plants, the angiosperms. Flowering plants began to flourish, and by the end of the Cretaceous, they dominated many ecosystems. Fossilized pollen reveals a dramatic surge in diversity between roughly 180 million years ago, and within that landscape, a massive figure moves forward. More than 9 meters long, weighing over 5 tons, this is Parasaurolophus, which lived approximately 76.9 to 70.5 million years ago. CT scans reveal that its elongated crest housed a complex system of twisted air passages, capable of producing low-frequency sounds as air moved through them. But how could a 5-ton body survive on plants alone? Parasaurolophus possessed a dental battery of hundreds of tightly packed teeth, constantly replaced throughout its life. Then another giant appears, about 12 meters long and weighing between 5 and 6 tons. This is Edmontosaurus, which lived from roughly 73 to 66 million years ago. The success of Edmontosaurus was also closely tied to flowering plants. With a large digestive system likely relying on microbial fermentation to extract maximum energy from cellulose-rich vegetation. So what allowed these creatures to reach multi-ton scale? First, the Cretaceous climate was warmer and more stable, with no permanent ice at the poles. Atmospheric carbon dioxide levels were higher than today, enhancing photosynthesis. Second, high sea levels created vast coastal plains, ideal environments for lush vegetation. And third, predation pressure played a critical role, as theropods evolved to become larger and faster. Herbivores had to adapt in response. Massive size became a defensive strategy, harder to bring down and harder to consume. The abundance of plant life gave rise to gigantic herbivores. Now we move into the realm of the hunters, where evolution shaped not only immense size, but also strange anatomies, bold survival strategies, and scientific debates that continue to this day. Cretaceous theropods were no longer a single template. They branched, split, and experimented with some of the boldest survival strategies in the evolutionary history of dinosaurs. Let's begin in North Africa, about 95 million years ago, where an ancient river flowed across what is now the Sahara. There, a towering figure wades into shallow water. This is Spinosaurus aegyptiacus, one of the strangest theropods ever to exist. Its body length may have reached up to about 14 meters, with an estimated mass of around 7.4 tons according to updated 2022 studies. But what truly set Spinosaurus apart was not just its size. Along its back rose neural spines up to approximately 1.65 meters tall, forming a sail-like structure. Conical teeth, without serrated edges, further support that interpretation. Spinosaurus was not the ruler of dry plains. Meanwhile, in South America, around 71 to 69 million years ago, another predator emerged, Carnotaurus, measuring about 7.5 to 8 meters long and weighing between 1.3 and 2.1 tons. Carnotaurus had a streamlined body and powerful, elongated legs. Its short, robust skull and small horns above the eye sockets may have been used for display or head-to-head clashes during intraspecific competition. But diversification did not stop there. In Asia, a towering creature with strangely long arms moved slowly through dense vegetation. This was Therizinosaurus. Its claws extended more than 1 meter in length, among the longest ever recorded in a terrestrial animal. This was a plant-eating theropod, its small teeth better suited for cropping vegetation than tearing meat. And in a world where herbivores were growing larger and more numerous, theropods did not merely have to hunt, they had to compete with one another for territory and for prey. Next, we step into an era where not only predators, but also prey were armed with astonishing defensive adaptations, transforming the Cretaceous into a true age of evolutionary weaponry. On the plains of North America about 68 million years ago, the air is warm, vegetation thick, and in the distance, a massive, multi-ton body moves forward. This is Triceratops horridus, one of the final icons of the Cretaceous. Measuring about 8 to 9 meters long and weighing between 5 and 9 tons. Triceratops carried 3 horns on its head. The 2 above its eyes could reach nearly 1 meter in length, and behind them spread a bony frill up to about 2 meters wide. Histological studies show that the frill was richly supplied with blood vessels, possibly linked to thermoregulation or to color display when the animal was alive. Many Triceratops healed injuries on their frills and horns, punctures and fractures, consistent with horn thrusts from other individuals. Its back was covered in thick, rugged bony plates, osteoderms, and at the end of its tail swung a solid bony club. This was Ankylosaurus magniventris. Simulations estimate impact forces exceeding 6,000 newtons, depending on the velocity and mass of the tail club. Yet what is especially revealing is that not all ankylosaur individuals possessed a fully developed tail club when young. When population density is high, prominent features, longer horns, larger frills, thicker armor, can determine who passes on their genes. When we widen our view, we recognize a familiar evolutionary pattern. When environments are stable and resources abundant, competition shifts from pure survival to reproductive optimization. We leave behind the world of horns and tail clubs to explore another evolutionary leap within the theropods, where feathers, enlarged brains, and egg care behaviors open the path that will ultimately lead to modern birds. In the humid forests between 75 and 71 million years ago, a small shadow slips across a carpet of decaying leaves. This is Velociraptor, only about 1.5 to 2.07 meters long. Weighing just 14 to 19.7 kilograms, biomechanical analyses estimate it could reach speeds exceeding 40 kilometers per hour. Long legs, elastic tendons, and a sickle-shaped claw, about 6.5 centimeters long on the second toe. All of it formed a design optimized for swift, precise strikes. Yet it was a 2007 discovery that truly transformed how we see this animal. On fossilized forearm bones, paleontologists identified quill knobs, the attachment points for feathers, similar to those found in modern birds. In non-flying species, feathers serve for insulation, social display, and even balance during high-speed movement. If Velociraptor embodied agility, then Troodon became a symbol of intelligence. Large forward-facing eye sockets suggest stereoscopic vision and the ability to judge distance accurately. Oxygen isotope analysis from fossilized teeth indicates that Troodon's body temperature may have reached around 42 degrees Celsius, close to that of modern birds. A fast body, a relatively large brain, a sensitive nervous system. Was this the outline of an evolutionary branch that might have developed even further? Had history turned differently? Farther north, Troodon fossils have been discovered in Alaska, a region that once endured long, dark winter months. And then we encounter an even more moving image: fossilized nests, adult individuals positioned over clutches of eggs, arms spread wide. In that moment, the boundary between dinosaur and bird becomes fragile. They are no longer two separate worlds, but part of a continuous evolutionary flow. While some species pursued gigantism, pushing toward the physiological limits of size, smaller theropods followed a different path, increasing neuron density, refining vision, developing parental care behaviors. Yet before catastrophe would strike, the story of biology reaching its upper limits was already unfolding. We will step into that question next, where names like Argentinosaurus carry us to the edge of what once seemed impossible. Between about 96 and 92 million years ago, on a South American plain, the ground trembled beneath footsteps weighing tens of tons. This was Argentinosaurus huinculensis, one of the largest land animals ever to exist. Its estimated length ranged from 30 to 35 meters. Its body mass ranged from 65 to 80 tons. How could something of that scale survive? Look at the femur of Argentinosaurus. Fossil specimens show it may have reached about 2.5 meters in length. The bone structure was honeycombed, filled with numerous internal air cavities that reduced weight while maintaining mechanical strength. It wasn't just the bones. The respiratory system of giant sauropods is believed to have included air sacs similar to those of modern birds. And where did the energy come from to sustain a mass of 70 to 80 tons? Argentinosaurus may have needed to consume hundreds of kilograms of vegetation every day. Some estimates suggest intake could exceed 100 kilograms per day, depending on the nutritional quality of Cretaceous plants. Its long neck was not merely for reaching upward. It functioned as a biological crane. allowing the animal to sweep across a wide feeding area without moving its entire massive body. Fossils from Patagonia reveal the presence of large theropods, such as Maposaurus and Gigantismus, within the same geological formations. The global climate was warm, with no permanent ice at the poles, and atmospheric carbon dioxide levels higher than today, driving vigorous plant growth. As continents drifted apart, they formed ecosystems that were both rich and relatively isolated. Modern biomechanical models suggest that sauropod limb bones operated near their maximum safety threshold. If on-land evolution tested the limits of bone and muscle, then beneath the water it tested speed and strategy within a three-dimensional world. And that is where the story continues. In the Cretaceous oceans, where a parallel ecosystem was quietly writing its own chapter of evolutionary history. The Cretaceous was not only the age of dinosaurs on land, it was also a golden era for marine reptiles within a parallel ecosystem vast beyond imagination. Sea levels during the Cretaceous stood approximately 100 to 250 meters higher than today. Warm, nutrient-rich waters fueled explosive growth of plankton. And then, from the dark depths, a shadow more than 10 meters long glided past. This was Mosasaurus, not a true dinosaur, but a marine reptile belonging to the Mosasaur group. Living between about 82 and 66 million years ago, Mosasaurus could reach maximum lengths of around 13 meters. Conical, razor-sharp teeth and a flexible jaw structure allowed it to swallow large prey, from fish and squid to other marine reptiles. Imagine diving into a Cretaceous sea, schools of ancient fish moving in tight formations. Then, from a distance, a movement as fast as an arrow. That was Zephactinus, a predatory fish measuring 5 to 6 meters long, capable of reaching estimated speeds of around 60 kilometers per hour. Yet not every marine creature was built for speed. In another corner of the ocean, a strange silhouette drifted slowly forward. This was Elasmosaurus. Living about 80.5 million years ago, Elasmosaurus measured roughly 10.3 meters in length. What made it extraordinary was its neck, about 7.1 meters long, composed of approximately 72 cervical vertebrae, a number that seems almost unimaginable. Evolutionary pressures here differed from those on land. Water supported body weight. allowing for larger sizes without the structural burden faced by terrestrial giants. An intriguing detail is that many marine reptile groups, such as mosasaurs and plesiosaurs, represented independent evolutionary branches, yet coexisted within the same era. This reveals that the Cretaceous was not merely the age of dinosaurs, but an age of planetary-scale biodiversity. Ask yourself, if you lived at the end of the Cretaceous, how would this world feel? On land, valleys filled with dinosaurs. Beneath the sea, predators stretching over 10 meters long, no humans, no engines, only wind, waves, and the primordial pulse of life. The composition of plankton communities shifted. Certain groups of marine reptiles began to decline in diversity. The ocean, though seemingly calm, was in reality a system deeply sensitive to climatic and geological change. And as global shifts accelerated, from large-scale volcanic activity to fluctuations in sea level, both terrestrial and marine ecosystems were drawn into the same vortex. We now return to the apex of the continental food chain, where an iconic name ruled the final years of the Cretaceous. But alongside that dominance, had ecosystems already begun to weaken before catastrophe struck? Across the coastal plains of North America, between 72.7 and 66 million years ago, one predator stood at the absolute summit of the food chain: Tyrannosaurus rex. Its estimated average mass was around 8.8 tons, and its skull alone stretched over 1.5 meters in length. Biomechanical models suggest its bite force could exceed 35,000 newtons. Some estimates even higher, powerful enough to crush the thick bones of large herbivores. CT scans of its skull reveal an enlarged olfactory region, indicating an exceptionally acute sense of smell. Forward-facing eyes provided stereoscopic vision, allowing precise depth perception during an attack. Growth ring analysis in fossil bones shows that juveniles experienced extremely rapid growth. It was a biological machine optimized to reach maximum size in a remarkably short time. Yet even at that pinnacle, was the late Cretaceous ecosystem truly flourishing? Or had it already begun to weaken before catastrophe struck? Some studies based on fossil data from North America suggest that the diversity of certain dinosaur groups may have shown a slight decline in the final few million years of the Maastrichtian. Meanwhile, Earth itself was undergoing major upheavals near the end of the Cretaceous. Imagine vast layers of lava, tens of meters thick, spreading across the landscape, releasing enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere. Carbon dioxide intensified the greenhouse effect, warming the climate. Sulfur dioxide could form sulfate aerosols, reflecting sunlight and triggering temporary cooling. Oscillations between warming and cooling, acid rain, and shifting sea levels all placed mounting stress on ecosystems. Carbon isotope analyses from marine sediments reveal disturbances in the global carbon cycle during the late Maastrichtian. This suggests disruption in oceanic biological productivity, the foundation of the marine food web. If plankton populations declined, small fish would follow. And from there, the entire ecological network would feel the impact. On land, sea levels showed a downward trend compared to earlier Cretaceous highs. Inland seas retreated, habitats shifted. Coastal plains, home to many dinosaur species, were restructured. So the larger question remains, were T-Rex and its contemporaries living in a world already under strain? Some scientists argue that dinosaurs remain diverse and well adapted right up until the boundary 66 million years ago. In North America, formations such as Hell Creek still reveal a rich presence of multiple groups. From large herbivorous dinosaurs to early marsupials, turtles, crocodilians, and ancient birds. There is even evidence of cannibalistic behavior in T-Rex, bite marks on the bones of individuals from the same species. This may reflect intense competition or simply opportunistic feeding within a complex ecosystem. But it also suggests something deeper. Even the apex predator is never immune to survival pressures. Imagine standing in a riverbank forest at the very end of the Cretaceous. T-Rex still walks, hunts, reproduces. Herbivores still move in herds. The oceans remain filled with massive predators. If ecosystems were slowly declining, then the catastrophe that followed was merely the final blow to an already weakened system. If ecosystems were slowly declining, then the catastrophe that followed was merely the final blow to an already weakened system. But if life was still thriving, then what came next was not the quiet ending of a fading dynasty. It was the sudden collapse of a world at its peak. Two interpretations of the same moment in history. The apex of the food chain always depends on the smallest links beneath it. Chicxulub was not merely an impact crater, it was the boundary between two eras. Was it the definitive end of the age of dinosaurs, or the doorway to an entirely new chapter of life? After the dust settled and the light returned, the world was no longer the same. No more creatures weighing dozens of tons dominated the land. Ecological niches stood empty, and within that void, mammals, once small, shadow-dwelling survivors, began to diversify rapidly. Within 10 million years after the impact, both the number and size of mammals increased dramatically, paving the way for primates, and eventually, for humans. But what if that asteroid had arrived a few minutes earlier or later? What if it had plunged into the deep ocean instead of striking the sulfate-rich rocks of the Yucatan? Climate models suggest that the geological composition at the impact site played a critical role in injecting sulfur into the atmosphere, intensifying global cooling. Had the conditions been different, the scale of extinction might not have been so severe. The universe is not merely a distant expanse filled with stars. It is an active force that intervenes directly in the biological history of this planet. The Chicxulub event reminds us that Earth is not a closed system. We live within a dynamic solar system where celestial bodies continue to move, collide, and sometimes change everything. Today, global programs track near-Earth objects, or NEOs. We scan the skies not out of curiosity alone, but because the lesson from 66 million years ago still holds. History has shown that evolution can flourish brilliantly for hundreds of millions of years and collapse in a matter of days. Is life always balanced between fragility and resilience? Could it be that impacts emerging from the darkness of space are the very engines that drive the greatest evolutionary leaps? As we close our journey through the Cretaceous, the golden age of dinosaurs, we realize this story is not only about extinction. It is about continuity, about how life restructures itself after catastrophe, about how, from the ashes of an old world, a new one is formed. And perhaps, somewhere out there in the depths of space, similar stories are still unfolding. Other planets, other ecosystems, other beginnings and endings, waiting to be discovered. Thank you for staying with WUFO Space until the very end of this journey through the vast universe. If you found this video interesting and insightful, don't forget to like, share, and subscribe to WUFO Space so you won't miss our next cosmic adventures. Your support means the world to us and fuels our passion to keep exploring the wonders beyond.